Welcome to this special edition of Frequency Matters, the RF and Microwave Update Series. I'm Pat Hindle. I'm here with special guest Tom Kole, Vice President of Sales and Marketing, and Gabriele Formicone, Director of Technology and Innovation, both from Integra Technologies, Inc. Welcome, guys.
Thanks, Pat.
Thank you, Pat.
So can you tell us a little bit about Integra Technologies and how you differentiate in your markets?
Absolutely. Integra has been around for about 21 years. And what's unique about our company is we focus mainly on very high power. So as we call it, power with a capital P. The focus that we do that's different than others is really high performance, avionics, radar, those types of markets. But what's unique about us is that we have a semi-custom approach. And that's something unique in the industry where we will focus our IP and our building block transistors and packages and so forth, and we will put those together for a customer to do a unique solution very quickly, very cost effectively. And that's, in this day and age of larger companies coming together, a very unique aspect.
So you've developed a very exciting new high voltage GaN on silicon carbide process and technology. Can you tell us how you went through that development and if it was spurred by any particular gaps in the marketplace?
Absolutely. Integra has been servicing, if you want, or pioneering high voltage RF, high power RF solutions for decades. We looked at the marketplace. There is a growing need, if you want, to replace vacuum electronics devices with solid states. Right. And to the point that even the Department of Energy, several agencies has been allocating funding for driving this type of innovation. If we looked at, I think even the 2019 DoD budget is setting funds for to foster this type of activity. We looked at the technology landscape on the solid state front. What we see achievable nowadays with the state-of-the-art 50 volt, 2850 volt RF gallium nitride is about 1 kilowatt plus type of devices. And when we're dealing with substituting or replacing megawatts type of devices serviced by Klystrons, TWTs, vacuum electronics in general, it's a big leap. So Integra has been pioneering some new solution that could better serve this type of technology transition. And what we have come up with is a new version, if you want, a derivative or to a certain degree, a redesign of the high voltage RF gallium nitride, still based on silicon carbide substrates. What really we focus on with this technology, rather than design devices that work at 50 volts, we're exploring operation at 100, 150 volts. Wow. We achieve several objectives while doing that. First of all, it's not what we see in power electronics. There are high voltage capable power electronics devices that work in the kilohertz frequency range. This design is really targeted for RF microwave type of application. With operation at 100, 150 volts, what we get is a higher power density, typically in the 10 to 20 watts per millimeter, depending on whether it's a pulsed CW operation. The beauty of it is that it really comes with a high impedance. When we increase voltage, we also achieve higher impedance. And the two, higher power density, higher impedance, kind of work together to overcome the limitation of the 1 kilowatt type of maximum power achievable with 50 volts technology. We get gallium nitride properties allows for low output capacitance per watt of RF power. This feature is critical to be able to take advantage of harmonic tuning. That's what we need to combine with the high voltage, low capacitance to achieve high efficiency at the same level. And I think one of the key points of this technology is also that it's really based on the gallium nitride on silicon carbide supply chain. Right. So it does not involve maturing or developing new material system, which, something like gallium nitride on diamond or some other exotic material that are being developed more on the fundamental R&D type of roadmap that we see funding through university and so on. So this approach would be able to create something that has more power. We can achieve building blocks of a few kilowatts or several kilowatts depending on the mode of operation. And in that regard, it's a better match for transitioning and replacing vacuum electronics with a solid state, more robust and more reliable alternative.
So you are targeting just the really high power RF. What is the ultimate that this process can achieve, and how do you address the thermal issues associated with these really high power densities?
Absolutely, I can answer that. Integra has been working on this development for at least the last 5 years. We have optimized the AP design, die design, field plates, drift region. We've also looked at several gate lengths from 1 micron, half micron, quarter micron. We also have published results in this type of development. And we have demonstrated power density from 10 watts to 20 watts per millimeter, from UHF to LS, probably C and X bands. One of the examples I can mention, some of the latest developments, we have designed to build 50 millimeter single devices, this is single die, that we have characterized over several frequencies in the UHF type domain. We've seen that with this device can operate at 100 volts in CW mode and generates more than 500 watts output power.
That's impressive.
We can also operate at 150 volts in pulse mode to achieve with the single die over 1 kilowatt. I think Integra's design team has done an outstanding job to match the harmonics and achieve 80% efficiency. Within this framework, we achieve over 20 dB gain. And yes, there is a concern about how do we extract the heat. However, Integra, besides high voltage GaN on silicon carbide, has also been exploring innovative solutions on the thermal management side, and has basically been able to patent a technology, a thermal enhancement technology approach, which allows heat extraction from the active region of the die to extract it laterally and still dissipate it on the bottom flange of the package. So we don't need a top heat sink in the device. The technology does not rely, if you want, on graphite or diamond matrix type of composites as for heat spreaders. Also does not necessarily rely on these copper flange type of packages. However, these derivatives or improvements in package and assembly technology can definitely be added to what we have. Right. To the point, I envision that we probably could run with this type of addition. We could probably run at 150 volts, maybe in CW mode, and still be able to achieve junction temperatures below the 200 degrees C type of level, which is needed for good reliability, long-term reliability, and MTTBF. I would say that it's at this point we have achieved good results demonstrated across several frequency bands. We are working on scaling up the technology, trying to go beyond the demonstration and use more than one die in a larger package to really end up with what we want, which is a multi-kilowatt single-ended devices, which really will transform the transition from vacuum electron devices to a solid state alternative.
Yeah, absolutely. I mean, you've really designed everything. You've optimized the design at the chip level, the package level, and everything, so works well together. So can you tell us about what benefits it has at a system level, and then any future plans you have for this technology?
Yeah, what gets us really excited about the high voltage GaN is the prospect of really shattering the barrier for traveling wave tube and the vacuum electron device tube replacement. That has been something that has been the aspiration for a long time, but when you try to build building blocks in the kilowatt range versus what Gabriele's technology development in the high voltage realm could do, we can now have cells that are 4 kilowatt transistors. So if you're trying to build an avionics system, which is typically 8 kilowatts, would you rather combine 10 devices, or would you rather work with one device and do a simple combination push-pull to get the ultimate power level you're achieving? That's the leap ahead that we're really targeting with the high voltage GaN. Instead of incrementally moving a couple hundred watts, we want to go and make it integer multiples. So if you think about very high power traveling wave tubes that are in the 50 and 100 kilowatt realm, if you take a look at what our devices can do, if we have a much larger power cell, now you're talking about reducing the number of combinations from hundreds of devices to 20s of devices. And that's where we get really excited, because every level of combining that goes away means efficiency that's added. So this is really the enabler that we think will leapfrog us ahead in terms of a solution for these very large traveling wave tube replacement opportunities.
Well, great. We really appreciate you guys joining us today and supporting this interview. We appreciate it very much.
My
Thanks,
pleasure.
Pat.
Thank you.
And we hope everybody will join us for the next Frequency Matters.